I will give it a couple more minutes, Jane.
Sounds good.
Okay, you ready, Jane?
Sure. Yeah, I'm good to start.
Okay. All right, well, good afternoon, everybody, or morning on the West Coast where Jane is today. Welcome to this week's CDAC hosted webinar from the University of Illinois in Chicago. Today, we're really pleased to welcome Jane Herriman for today's webinar. Jane is a technical consultant with Livermore Computing at Lawrence Livermore National Lab, where she works to support scientific research through high performance computing. And she carries out workshops and teaching people in getting users up to speed on some of the high performance computing capabilities available at Livermore. Jane received a dual bachelor's degree in chemistry and French at Carnegie Mellon University, and then received her PhD at Caltech, working in the research group of CDAC partner Brent Foltz. Jane presented several outstanding posters at the annual SSAP Symposia during the time she was a graduate student. Jane will be talking about theoretical work, computations today, but she's done both experiment and theory during her graduate work, having worked on a variety of projects at the APS with her Caltech colleagues, in addition to her computational work on phonon thermodynamics, which she'll be discussing today. During her time as a graduate student, she was a Lawrence Graduate Scholar and carried out her research in the quantum simulations group at Livermore. Jane also took some time out to serve as the Director of Diversity and Outreach at Julia Computing, where she worked on curriculum development, teaching, and community and event organizing. Jane has a history of work in outreach, having served as a French department tutor and with French department outreach at Carnegie Mellon, as well as a math and reading tutor to middle schoolers in her community. Jane has won several prestigious awards. I'll just mention a couple of them. She won the Julia Community Prize, and she also won a Department of Energy Office of Science Graduate Fellowship. She won the J. Paul Fugazi and Linda Monteverdi Award, a Caltech Clark Fellowship, a Fulbright Research Fellowship, and she was also elected to Phi Beta Kappa. She was an Andrew Carnegie Society Scholar and won the Carnegie Mellon Chemistry Departmental Award as an undergraduate. And today she's going to be talking about some of the work she did as a graduate student on the phonon thermodynamics of gallium nitride and gallium arsenide. Welcome, Jane Herriman.
Thank you, Steve. All right, hi everyone. So as Steve mentioned, this is my dissertation work that I'll be going over. The rough structure of the talk is that I will be going over an introduction, and the intro for this is pretty long because I want to sort of get everyone on the same page with the concepts that I'll be going over. And then I'll then talk about two classes of results from my dissertation work, those on elastic behavior and those on phonon thermodynamics. And then I'll summarize some of the main conclusions at the end. So throughout the intro, I'm going to be returning to the title of my dissertation as I try to break it down. So in particular, I'll define the materials that I worked on, the properties that I studied in those materials, and how I calculated the conditions under which I studied those properties. So when we think about humanity's technological advances, whether we're talking about like engine technology or weaponry or the personal computer, solar panels, or LEDs, we see that those technological advances have been enabled by advances in materials, like the metals or the semiconductors from which they're built. So these material advances are enabled by an understanding of material properties. Knowing how and why a material behaves under certain conditions, such as particular temperatures or pressures, or in response to stimuli like maybe a pulsed laser or a shock wave, can allow us to pick the best material for a given application and also to engineer new materials. Now, in order to study material properties and ultimately choose the best material for a given application, we need appropriate models of those materials and their properties that allow us to predict and understand them. And then perhaps it should go without saying, but these models are only useful when they are applicable, when they actually work to capture the properties that we want to predict or understand. And this is really the driving force for much of the work that I'm going to be showing today. We want to better understand when certain commonly used models or approximations actually work and when they fail. Now, for the most part, the material properties that we'll consider will be determined by the atoms of those materials. In particular, we can understand most material properties if we know which atoms are in the material, so the chemical or the isotopic composition, where those atoms are, so the structure of the material, and what the atoms are doing, or the lattice dynamics of the material. Now, for illustration, a material might consist of atoms of one or more elements, here represented by different colors. So maybe tan represents gallium atoms and blue represent nitrogen atoms. Those atoms can then adopt different structures or different atomic arrangements. So now on the right, we see that our atoms have adopted a hexagonal lattice, whereas they're in some sort of cubic lattice on the left. As for what atoms are doing, they vibrate around their equilibrium positions, but they vibrate in different ways under different conditions and depending on the structure and chemical composition of the material that they're in. So in my work, when we ask which atoms, the answer is gallium and nitrogen or gallium and arsenic. And then when we ask where are they, the answer is that the atoms will fall into either the wurtzite or the zinc blende lattice, where wurtzite is a type of hexagonal structure and zinc blende is a type of cubic structure. So between these two chemical compositions and these two structures, we define 4 different materials that we're going to look at in this work. So these are the materials that I'm talking about when I refer to gallium nitride and gallium arsenide. And then the final question of, what are those atoms doing relates to phonon thermodynamics and the elastic behavior of these materials. So let's start by talking a little bit about phonon thermodynamics, and in particular asking what is a phonon. So I already mentioned that the atoms of materials are always vibrating around their lowest energy positions. And it turns out that we can break these vibrations into individual or quantized vibrations that we call phonons. So each of the GIFs on this slide shows a different phonon mode in gallium nitride. Now in real life, if we could zoom in on a material and see how an atom was vibrating, its movements would be a lot more chaotic than any of the movements shown here, because real life movements would be a combination of many, many distinct vibrational patterns, like the more simple ones shown. So we can think of these phonons as waves that pass through material, causing the atoms to oscillate as they go by. And we're able to study the phonons in a material by modeling our materials with a ball and spring model. So we like to pretend that nearby atoms are really connected to each other by springs, and that the springs are what actually govern the atomic movements. Now we can describe these atomic movements in terms of force constants. shown in the equation at the bottom of the slide is phi, that contribute to the total energy of a material. So at the bottom of the slide here, I show a model Hamiltonian operator that gives the total energy of a system by accounting for some internal energy, shown as U naught, added to the kinetic energy of the atoms as they move around, and then the potential energy stored in the imaginary springs that bond atoms together, again, where those springs are described by these phi or force constants. So when we talk about phonons, I want to familiarize you first with the types of data that I'll be showing. So first, I'm going to be talking about phonon densities of states, which looks something like this. Whenever you see a plot that looks roughly like this, we have the frequency of possible phonon modes shown on the bottom or the horizontal axis. I'll often use frequency and energy interchangeably when I talk about phonon effects because those quantities scale together. And then on the vertical axis, we have the relative number of states or possible phonon modes that can exist. So this gives us a read on all the possible vibrations that can exist in a material as a function of frequency. So if the peaks in a plot like this move to the left, I'll say that they are softening as they decrease in energy. And if peaks move to the right, I'll say that they're stiffening as they increase in energy. Okay, so one metric for quantifying the degree to which a phonon energy goes up or down is a Grüneisen mode parameter. So here in this definition for a mode Grüneisen parameter, gamma sub I is the Grüneisen mode parameter for a phonon I, where V is the volume and omega is the frequency of that phonon I. So the important bit here is the partial derivative of omega with respect to volume, showing us the Grüneisen parameters quantify the degree to which phonon frequencies shift with volume. Now in this other type of spectrum that we'll be looking at called phonon dispersion relations, phonon frequencies are now shown on the vertical axis. And now on the horizontal axis, we have different directions or paths through the momentum space of the crystal. So that gives us information about directions and wavelengths of possible waves in a material. So phonon dispersion relations give us more detailed information than the phonon densities of states, but only about particular phonon modes. So we get both like more and less information in different ways. Now this time, because frequencies are on the vertical axis, if we see an increase in energy or a stiffening of phonon modes, our lines are going to move up rather than to the right as before. And a softening will be shown by having lines move down as energies or frequencies decrease. And a good way to better understand connections between the phonon dispersion relations and the phonon densities of states, or DOS, is to flip the DOS on its side so that the frequency axes of the two different types of plots line up. So then we can see that the individual branches shown in the plot on the right contribute to peaks that we see on the left. And the gap that's shown on the left is the same as the gap on the right. Another point to make is that our spectral frequencies should always fall above zero. So if phonon frequencies fall below zero, they become imaginary, and that indicates that something's wrong, like maybe the material has gone unstable. At times, I'll show you phonon dispersion relations that look sort of like this, where the lines in the plot are shown to have variable thicknesses. So these types of plots show the line widths of given phonon modes. Here, line widths come from something called the phonon self-energy, in this equation shown as gamma, and they're inversely proportional to phonon lifetimes denoted by tau. So if we think of a spring that gets pulled or compressed and then starts to vibrate, at first that spring is going to oscillate back and forth, but then the vibration will eventually start to die out or dampen until the spring stops moving. Similarly, vibrations in a material will dampen or die out, and the phonon line widths, or the thicknesses of the lines shown in the plot here, indicate how quickly the vibrations in a material dampen, with thicker lines indicating that the phonon dies more quickly. Okay, so that was my intro to phonons, and I want to talk now a little bit about elastic behavior, in particular, giving an intro to elastic constants. So to talk about elastic constants, first let's imagine that we have some material that we can represent with a unit cell like this, which has a few atoms inside it. And let's say that this material starts at its lowest or equilibrium energy, which I'll call E of 0. Then we apply some strain to the material denoted by epsilon bar, which distorts the material and causes the material to now have an energy of the strain tensor epsilon bar. So if we look at the change in energy induced by the strain and normalized by the volume, we can express that energy difference in terms of partial derivatives of the energy with respect to the strains. So these energy derivatives are equal to our elastic constants, here denoted on the far right as C sub ij. So these elastic constants give us a way to quantify a material's energetic response to different types of strains or deformations. These elastic constants are actually related to our phonons in something called the long wavelength limit. So we tend to think or talk about elastic constants, Cij, when we're thinking about macroscopic materials, or when the vibrations that we consider have wavelengths so long that the distances between atoms look really tiny. So in our phonon dispersion relations, the gamma point in our momentum space on the horizontal axis there, it represents a point where we're considering infinitely long wavelengths. So the slopes of the straight branches very close to and coming out of the gamma point are in the long wavelength limit, and they represent information about very low energy, long wavelength phonons that we can connect to the macroscopic elastic constants. Furthermore, we could take our elastic constants and use them to construct a dynamical matrix M, of which the eigenvalues would then be density scaled phonon frequencies in the long wavelength limit. And knowing this relationship between elastic constants and phonon branches is important because it gives us some intuition if we're trying to connect phonon and elastic properties. So all of that wraps up my intro section on the properties that I consider in this work. Next, I want to talk to you a little bit about the conditions that I look at and how I account for those. So in particular, I'll talk to you first about temperature and various temperature models that are used in studying phonon thermodynamics. So we'll talk about harmonic approximation, the quasi-harmonic approximation, which builds on harmonic approximation, and then something called explicit anharmonicity, which doesn't fit into either of those first two models. Okay, so starting with a harmonic approximation. So in a harmonic approximation, maybe we start with a 1D harmonic oscillator in which we can imagine a weight here, a blue circle attached to a wall of infinite mass by some spring. And a harmonic oscillator follows Hooke's law, which is F, the force, equals negative kx, where x is the displacement. So this means that if we compress or stretch the spring, we'll generate a restoring force that's linear with the size of the displacement. So the more the spring is compressed or stretched, the harder it pulls on the weight to return to its original position. This also means that once the spring is oscillating, it will oscillate forever, and those vibrations will never dampen. So of course, some springs will be harder to stretch than others, and this spring constant K in the equation shown here tells us how stiff those springs are. Now, given these restoring forces, the potential energy of the spring is going to be quadratic with displacement, where here I'm showing potential energy with U. So when we use a harmonic approximation to model materials, we pretend that the atoms of material are connected by harmonic springs, such that the phonons in a material would never decay. And this leads to a term in the total energy of the material that is also quadratic with its displacements, here shown on the far right, on the bottom of the slide. Okay, so there are several problems with a harmonic approximation. For example, the assumption that phonons will never decay makes the phonons completely independent of temperature, and that leads to assumptions like, thermal expansion never occurs. So, for example, heat would never cause your power lines to sag on a hot day. Now, the quasi-harmonic approximation tries to partially fix this by admitting that thermal expansion does in fact occur. In a quasi-harmonic approximation, we continue to assume the material consists of atoms that we can think of as being connected by these harmonic springs. So still in a quasi-harmonic approximation, phonons are never going to decay, and we'll still get unrealistic predictions like infinite thermal conductivity. But we do acknowledge that phonons will change with temperature because thermal expansion will occur. And the phonons will be different for materials with different interatomic spacings. So in working with a quasi-harmonic approximation, we're saying that whenever we want to account for some property F and how it changes with temperature, we can do that simply by figuring out how the property F changes with volume, where we consider volumes that correspond to our temperatures of interest. We can better understand the problem with the quasi-harmonic model's assumptions by looking at the energy of a harmonic spring. So the trouble is that this relation works mostly when X, the displacement, is small. And then when temperature increases, the displacements X are also going to increase. So I show that with the GIFs that I have here, where the atoms on the right have larger displacements, as you might expect at higher temperatures. And so the harmonic and the quasi-harmonic model's assumption that phonons never decay will fail, and frequently, it will frequently more significantly, it will fail more significantly at elevated temperatures. So as a result, the quasi-harmonic approximation frequently fails to accurately account for thermal expansion. It will mispredict phonon frequency shifts, and it completely misses phonon decay. So it's unable to calculate real thermal conductivities. So whenever we see a temperature effect that is not accounted for by a quasi-harmonic approximation, one that is not simply a result of an underlying volume change, we call that effect explicitly anharmonic. So in my work, I used a method and a software package called the temperature-dependent effective potential method to capture explicitly anharmonic temperature effects. So I'll go over a little bit of how TDEP works. TDEP recognizes that as temperature increases, the local environment of an atom in a material is going to change. So in this schematic, I'm trying to depict atoms moving around their lattice sites with increasingly large amplitudes as the temperature goes up. So the way a given atom on the lattice interacts with or feels its neighbors is going to change as temperature goes up, because its neighbors effectively take up more space by bouncing around within a larger area. So TDEP uses a model Hamiltonian to capture the energy of a material system using force constants of arbitrary order. In my work, I use TDEP to generate both second and third order force constants to account for temperature effects. So the second order force constants account for two body interactions, and third order force constants account for three body interactions. Now TDEP wants to solve for the temperature dependent force constants in order to calculate the phonon properties of a system. So to get these force constants, we need displacements from some temperature representative snapshots of where we expect atoms to be at a given temperature. So we'll take these displacements and feed them to an ab initio software program like VASP. VASP will then calculate the forces resulting from the displacements that we've induced. And then given the Hamiltonian that I showed on the last slide, we can relate our forces to the displacements that cause them via force constants, via the force constants that we want to calculate. And then when we pass these displacements and forces to TDEP, generating these force constants, that allows us to calculate phonon properties like the densities of states. Okay, so what about these displacements, and how do we actually get temperature representative snapshots or temperature representative displacements in a material? So I used I guess a feature of TDEP that allows us to do stochastic sampling. So STDEP, or stochastic sampling in TDEP, starts with a relaxed equilibrium material, and it then displaces the atoms to positions where we might expect to find them at a given temperature. And to generate force constants that we can trust, we really need to generate many such snapshots, all of which have different sets of atomic displacements. So as for how we actually get the displacements in a single such snapshot, so we do that by starting with the equation at the top of the slide. So we call it a temperature representative displacement of atom I, vector U sub I. Now vector U sub I sums over all 3n phonon modes in a material, taking a contribution from each of the phonon modes, here shown as U sub IS. So if we consider the contribution from a single phonon mode, U sub is, and how that contributes to the displacement of the ith atom. This expression for U sub is has three different terms. So first, on the very right, we have the eigenvector of phonon S. The eigenvector of a phonon mode tells you the direction in which the particular vibration pushes the atoms. And we're then multiplying that eigenvector by an amplitude A, or A sub is, and by a random number Z. So first off, that expected amplitude of the contribution from phonon S to atom I's displacement is shown here as the expectation of A sub is. Some of the notable features are that the amplitude is going to go down when the mass of an atom goes up, and that the amplitude scales with the phonon distribution. Here shown, the phonon distribution is N sub S. Now that distribution of phonons, N sub S, is a Planck distribution. So it's a Bose-Einstein distribution with degeneracy 1 and a chemical potential of 0. So the takeaway from this distribution is that phonon modes become more frequently populated with increasing temperature, and that the degree to which a phonon contributes to the displacement of an atom increases with temperature, and the likelihood that the phonon actually exists. Finally, this random number Z, it's a normally distributed pseudo-random number coming from a Box-Mueller transform. So we start with two uniformly distributed numbers, uniformly distributed pseudo-random numbers eta 1 and eta 2. And then this equation for Z pops out a normally distributed pseudo-random number. So this number allows us to sample an atom's position at some random place along its trajectory for a given vibration. And we can then generate many of these snapshots of an atom in different positions, which we can use to generate a canonical ensemble that samples the Born-Oppenheimer surface of a material. Okay, so I think this is the last section in the intro, but I wanted to talk about how I account for elevated pressures, which is a little bit less straightforward than altering the volume of a material computationally. So to account for pressure, we start by assuming that the free energy at a given temperature and volume, here F of T comma V, is the sum of the energy of the static relaxed lattice, or U sub naught, and the vibrational or phonon free energy at the corresponding temperature and volume. So in practice, we want to figure out how free energy changes as a function of volume at a given temperature. In practice, what I end up doing is I would run phonon calculations at many volumes for a given isotherm. So once I had the output energies resulting from my input volumes, I would fit these energies to a Birch-Moynihan equation of state. And this equation has four parameters encircled, three of which we plug into an equation for pressure. So I could use that fit to calculate pressure as a function of volume. And yeah, this is the equation for pressure, where P of V is what we want at the end of the day. So once I had those pressure volume relationships, like the one that's shown in blue on this slide, I can figure out the volumes of the pressures that I wanted to work out. So if I wanted to, sample and look at phonons at 0, 10, and 15 GPa, for example, I could figure out what volumes I needed to look at with this pressure volume relationship. Okay, so that is the end of the intro, having walked through all of the jargon that's in my dissertation title. So I wanted to talk next about the first results section on elastic behavior in gallium nitride and gallium arsenide. So things we'll see in this section include how some stability conditions called the Born stability criteria work in gallium nitride and gallium arsenide. We'll see how the Born stability criteria predict lattice instability in gallium nitride and how they fail to capture the onset of instability in gallium arsenide, where phonon instabilities happen first. So in short, we will see that the Born stability criteria can't always be trusted. So starting with the Born stability criteria, these give us a way to determine the pressure at which material becomes elastically unstable. Once the Born stability criteria fail, a material can no longer exist, so it ceases to even have metastability. This is how we typically express the Born stability criteria. They're based on a set of coefficients, B sub ij, which are pressure shifted values of the elastic constants that we discussed earlier. Again, these elastic constants, Cij, describe a material's energetic response to strain. So the Born stability conditions vary by crystal type. For cubic crystals such as zinc blende, these three relations have to hold in order for a material to be elastically stable. And then for hexagonal crystals, there are three relations shown towards the bottom of the slide now. So in this plot, I'm visualizing the failure of the first two Born stability criteria to fail in gallium nitride. So values of the coefficients B sub ij are on the vertical axis in both subplots, and pressures are on the horizontal axes. So we have Wurtzite data in the top panel, zinc blende data in the bottom panel, and in both subplots, a stability criterion fails when purple and blue lines cross. So we can identify the reason for material failure and the pressure of that failure by seeing if either the solid or the dotted lines cross first. Now in Wurtzite gallium nitride up top, the solid lines cross before the dashed lines or at lower pressures, indicating that the material first goes unstable when that coefficient B sub 44 crosses the zero line, and that happens at 65 GPa. On the other hand, in zinc blende gallium nitride, the dashed lines cross first. So that indicates that there's some tetragonal shear instability at 40 GPa, which is where B12 first exceeds B11. So in gallium arsenide, I plot the stability conditions in a slightly different way. Again, we have pressure on the horizontal axes, and Wurtzite data is in the top panel, whereas zinc blende is in the bottom. This time, each condition is given a different line, either orange or blue, which fails when it crosses the zero line in black. So here, the Born stability criteria predict that Wurtzite and zinc blende gallium arsenide fail for the same reasons as their corresponding phases in gallium nitride. Again, the Wurtzite phase is predicted to collapse when B44 is no longer greater than zero, and the zinc blende phase is predicted to collapse due to a tetragonal shear instability when the coefficients B11 and B12 cross. This time, however, we have some other effects that are not accounted for by the Born stability criteria. So in particular, note that I have this in the top subpanel. I have a dashed orange line where I've omitted data around 20 GPa in the Wurtzite phase. So I've omitted that data because there were some oddities in the elastic constant data that I want to dig into and bring a little bit more attention to. So on this slide, I've plotted elastic constant data for Wurtzite gallium arsenide and zinc blende gallium arsenide against pressure. So pressures on all the horizontal axes here. Now the top 5 panels are for the elastic constants in Wurtzite gallium arsenide, and the bottom 3 are for the 3 elastic constants in zinc blende gallium arsenide. So what you'll see is that most of the trends here look smooth. But again, notice that I've omitted data for the top 2 subpanels, the panels for C11 and C12. So if I include that data, we see that there's a weird dip and spike in the elastic constant values. So I used VASP to calculate the elastic constants shown on this slide, and it turns out that the dip and the spike, here sort of accentuated on the right side of the slide, those are a side effect of the way that VASP calculates the elastic constants, given that there's actually a phonon instability occurring at these pressures. So in the plot to the right now, we see enlarged images of both the dip and the spike. Below that, there are phonon frequencies at the gamma point, falling to 0 and then going to imaginary values in the same pressure regime. And that's indicating a phonon instability. Now, to get a better sense of what's going on, we can look at the phonon dispersion relations in Wurtzite gallium arsenide at various pressures at 0 Kelvin. So here we have increasing pressure as we go from blue to purple to pink. So if we look at the gamma point and then consider the movement of so yeah, we have these V-shaped branches coming out of the gamma point, and then there's this relatively flat branch that crosses the V. If we consider the movement of those relatively flat branches, we see that as we go up in pressure from blue to purple to pink, the purple and the pink modes are decreasing in frequency. This is the same drop in frequency that we saw in the last slide that led to an instability. So let's see. The new information that we get from the spectrum, however, is that there's an additional phonon instability occurring at the M point in momentum space. So this instability precedes the phonon instability at gamma, driving material failure at a lower pressure. There was no hint of that in the elastic constant data, where we're looking only in the long wavelength limit. And that's what the Born stability criteria are based on. So next, if we look at the phonon dispersion relations of zinc blende gallium arsenide, we see another phonon instability occurring at pressures before the Born stability criteria fail. Here at the X point, we see that phonon frequencies are dropping rapidly until they fall below the 0 line and become imaginary. So at the L point in zinc blende gallium arsenide, we see frequencies dropping quickly, but really the first phonon instability that we have evidence for in zinc blende gallium arsenide happens at X. The Born stability criteria are normally used to calculate the range of pressure in which a material is elastically stable. But because they're based on the elastic constants and thereby the behavior of long wavelength phonons, they miss the behavior of shorter wavelength phonons that are away from the gamma point. Here we are seeing that the Born stability criteria fail to predict the onset of lattice instability in both wurtzite and zinc blende gallium arsenide. But all of this uses 0 Kelvin data. And the onset of the instability might change with temperature. So to estimate how the onset of instability might be impacted by temperature, I use mode Gruneisen parameters. So on this slide, I have Gruneisen parameters for the modes that first become unstable, plotted against pressure in GPa on the horizontal axes. So on the top panel, we're looking at mode Gruneisen parameters for one of the transverse acoustic modes at the M point. And in the bottom, we're looking at a transverse acoustic mode at the X point. Okay, so Gruneisen parameters tell us how the frequencies change with volume. And so here they give us an idea of how quickly certain phonon branches approach a frequency of 0 and become unstable. So for each material, I have a Gruneisen mode parameter plotted at 3 different temperatures, 0, 600, and 1200 Kelvin. And what we see here is that pressure causes the lines shown to curve less with increasing temperature. So this indicates that with increasing temperature, phonon modes are less sensitive to pressure. And at increasing temperatures, the phonon modes first exhibiting instability will progress towards that instability more slowly with increasing pressure. So this means that temperature is partially stabilizing our phonon instabilities. Unfortunately, we don't have enough data here to know if the Born stability criteria become relevant again when we're at higher temperatures in gallium arsenide. So takeaways from this section include that in gallium nitride, the wurtzite and the zinc blende structures are no longer stable after the Born stability criteria fail at 65 and 40 GPa. In gallium arsenide, the Born stability criteria don't work to predict material failure. And at 0 Kelvin, shorter wavelength phonon instabilities drive the materials unstable at about 18 and 20 GPa, where I first show these vertical purple lines overlaid with the plots on the right. Now, additionally, temperature partially stabilizes these phonon instabilities, pushing them to higher pressures at elevated temperature. An additional point to make here is that per the elastic constants and the Born stability criteria, we would expect material failure to be more similar based on structure, and that we'd expect wurtzite materials to fail similarly, for example. In practice, we might say that the actual types of atoms that we have are having a greater influence on material failure, as both phases of gallium arsenide have these shorter wavelength phonon instabilities that don't occur in gallium nitride. And now before I talk about phonon thermodynamics, I wanted to address another aspect of elastic behavior, which is the elastic anisotropy. So I quantified elastic anisotropy using the Universal Elastic Anisotropy Index, which is a superscript U. So this index provides a metric for assessing elastic anisotropy that works independent of crystal structure. This is in contrast to more traditional choices like the Zener ratio, which works for just cubic materials. So A superscript U is computed from the ratio of Voigt and Royce bounds on both the shear modulus G and the bulk modulus K. So the Voigt or the upper bound assumes isotropic strain, whereas the Royce or lower bounds assume isotropic stress. So I calculated these bounds on the shear and bulk moduli using the elastic constants. Now, in a perfectly isotropic material, these bounds are equivalent. So the value of A superscript U would be equal to 0. So on this slide, I have values for the universal elastic anisotropy index in gallium nitride plotted for both the wurtzite and the zinc blende phases versus pressure in GPa. And so we see that both materials become less elastically isotropic with increasing pressure. In a similar plot for gallium arsenide, we see that the elastic anisotropy increases with pressure for both phases of gallium arsenide as well. So we'll come to understand this a bit better after looking at phonon spectra in the next section. But for now, the takeaway here is that wurtzite and zinc blende gallium nitride and gallium arsenide all become elastically anisotropic with pressure. Okay, so going back to the main outline from the talk, let's go over phonon thermodynamics in these materials. In particular, let's start by looking at pressure effects on the phonons. So what we'll discuss here include how pressure drives the phonons in both gallium arsenide and gallium nitride in different directions, and then how this relates to elastic anisotropy. So we already got a sneak peek of the impact of pressure on the phonons in these materials when we considered phonon stability in gallium arsenide a bit before. So we saw that the two lowest energy phonon branches, called the transverse acoustic modes, are softening with increasing pressure. In contrast, all other modes stiffen with increasing pressure. So this includes the longitudinal acoustic branch, which is the third branch. If you're starting from the bottom of these plots, the longitudinal is the third branch emerging from the gamma point. So this cues us into why the elastic anisotropy increases with pressure. The elastic constants are related to the slopes of the three branches that come out of the gamma points. And as the phonon branches shift, differently or even in different directions, the material becomes less elastically isotropic. So net pressure effects are perhaps a little bit more clear if we start looking at, first off, only a few pressures at once, and then if we consider the densities of states rather than the dispersion relations. So let's do that for all four materials now. Here we have phonon density of states for gallium arsenide on the left, and then for gallium nitride on the right, with our wurtzite data on top in both subplots, and then the zinc blende are the two lower subplots. So in the plots on the left, let's look around 2 terahertz on the frequency axis, and we see that the highest pressure DOS in gray exists to the left of the lower pressure DOS. But then if we start looking at around 4 or 5 terahertz in those same spectra, we see that pressure has caused the gray peak to move to the right. So we see the same effect in gallium nitride in the right-hand subpanels by looking at the placement of the highest pressure pink curve relative to the others in each subpanel. So in the left part of the spectrum, still looking at the plots on the right, but the left part of their spectra, peaks are moving left, and peaks on the right side of those spectra are moving right with pressure. So just as in gallium arsenide, gallium nitride also has these transverse acoustic modes that move in the opposite direction of the longitudinal acoustic modes, and that heightens elastic anisotropy with pressure. Also, as a note, while we're comparing the densities of states of all 4 materials side by side, I like to point out a couple differences between the gallium nitride and the gallium arsenide DOSes. So first, we see that there's a clear band gap in gallium nitride on the right, whereas there's not a true band gap in gallium arsenide on the left. Second, the highest energy modes of gallium nitride are much higher than the highest energy modes of gallium arsenide. So our spectra in gallium nitride terminate around nearly 30 terahertz, whereas they terminate around 10 terahertz in gallium arsenide. In fact, we could look at the shifting of the highest energy modes in gallium nitride to high frequencies as the source of the phonon band gap. The reason for the phonon band gap in one atomic composition and not the other comes from the relative size of the atoms in these two systems. So in gallium arsenide, the two element types are much closer together in size, whereas in gallium nitride, nitrogen is much smaller than gallium. And this means that the nitrogen atoms in gallium they move around much more easily than their gallium counterparts. So the high frequency modes we see in gallium nitride are actually dominated by the relatively energetic movements of nitrogen atoms. Okay, but really the primary takeaway from this section is that pressure causes transverse acoustic modes in gallium nitride and gallium arsenide to soften, while all other modes, including the longitudinal acoustic modes, are stiffening, and that this drives increasing elastic anisotropy with pressure. So the next part of my results on phonon thermodynamics involves frequency shifting from temperature and pressure-temperature coupling effects. Okay, so what we'll see include how the quasi-harmonic approximation works better for gallium nitride than it does for gallium arsenide, and not only how a quasi-harmonic approximation fails to account for the effects of temperature on gallium arsenide, but how it fails to account for the sensitivity of gallium arsenide's temperature effects to pressure, with the takeaway being that you can't always trust the quasi-harmonic approximation. So first, let's look at gallium nitride, where the quasi-harmonic approximation worked relatively well. We might consider how increasing temperature by here 1120 degrees Kelvin might impact the phonons in gallium nitride at 0 GPa. Here, higher temperature phonons are shown in red and 0K phonons are shown in blue. So in both Wurtzite and Zinkblende, we see that the acoustic modes below the band gap don't change a whole lot with temperature. We see a little bit of mode softening for the optical modes above the band gap as the red lines above the band gap move below the blue lines. Comparing similar spectra for gallium arsenide, here given a 1200 degree boost in temperature, we see that the higher temperature curves in pink fall below those in purple more consistently. Now, while the plots here and those on the previous slide tell us about temperature effects, they don't tell us about the degree of explicit anharmonicity in these materials, because we don't know what fraction of these temperature effects would have already been accounted for by a quasi-harmonic model. So let's look at comparisons with a QHA or a quasi-harmonic approximation in each material, this time using the phonon densities of states. So if we go back to gallium nitride, looking at this 1120 degree Kelvin temperature difference, we can again compare the red and the blue lines. And now there is a dotted green line added that shows quasi-harmonic results. So if we want to see in this plot how well the quasi-harmonic approximation does with accounting for temperature effects, we can compare the red and the green lines. So we see here that the quasi-harmonic approximation is actually doing pretty well at accounting for frequency shifts at 0 GPa, because the green and the red curves are pretty similar. And while I'm not showing it here, results were comparable at other pressures as well. So this is all, zero GPa. On the other hand, so here, if we look for gallium arsenide at 0K curves shown in blue, with 1200 Kelvin curves shown in pink, and now add our quasi-harmonic approximations to 1200 Kelvin in purple, we see that when we compare the pink and the purple lines now, we see the impact of explicitly anharmonic temperature effects. And the offset between these lines say that the quasi-harmonic approximation is doing less well than it did in gallium nitride. More interesting is what happens when we add pressure. So if we look at similar plots to the ones up top at 0 GPa, now the bottom plots are for data at 10 GPa, we see that the quasi-harmonic approximation does much worse. So the quasi-harmonic approximation here appears much more similar to our 0 Kelvin DOS, and that offset between the pink and the purple line has grown. This shows that in gallium arsenide, pressure increases the impact of explicitly anharmonic phonon effects. Okay, so the takeaways for this section are first that the quasi-harmonic approximation accounts for most of the frequency shifts that we see with temperature in gallium nitride, but it's less successful for gallium arsenide. And in particular, explicitly anharmonic frequency shifts become much more important with increasing pressure in gallium arsenide. So this means that temperature and pressure effects are coupled in spite of what we might think given a quasi-harmonic approximation. The last result section that I have here is on temperature and temperature pressure coupling effects on phonon line widths. So what we'll see include the impact of temperature on phonon line widths and lifetimes, how it depends on pressure. And then we'll see that pressure causes phonons to dampen more slowly in gallium nitride and more quickly in gallium arsenide. Again, you can't always trust a quasi-harmonic approximation. So here I'm showing phonon dispersion curves for gallium nitride. In the top row, the two subplots are shown at 0 Kelvin. In the bottom row, they are shown at 1120 Kelvin. And then I've got Wurtzite data on the left in both cases and zinc blende data on the right. So in each plot, I've plotted the phonon dispersion relations with dotted lines, and then I've overlaid solid lines with thicknesses equal to the line width of the respective phonon modes. So the presence of non-zero line widths is always an explicitly anharmonic effect, because as you might recall, phonons live forever and they never dampen or broaden in a quasi-harmonic model. So here we see that the phonon line widths are basically 0 at 0 Kelvin and become somewhat more pronounced by 1120 Kelvin for the optical modes at least. But where our temperature data gets interesting in gallium nitride is when we look at how changes in our line width data differ at different pressures. So this plot looks a lot like spaghetti. So I'm going to try to just point out the relevant features. Okay, so first in black, I've plotted phonon line widths for each phonon branch at 0 GPa, or how the phonon line widths for each phonon branch at 0 GPa change with temperature between 0 Kelvin and 1120 Kelvin. So that's a change in the phonon line width at 0 GPa. So in the upper plot, if we on mode that had its line width increased by about 0.6 terahertz on the vertical axis. So that line width increase happened between 0 and 1120 Kelvin. Now I've plotted similar curves in green and pink for higher pressures in each of these structures. The important thing that you want to note on this slide is how the peaks change with increasing pressure, or how the lines in different colors are different from one another. So for example, the highest peaks at the gamma point shown here in each color are not only different sizes, but they're completely different shapes. And the reason that this is important goes back to our assumptions from a quasi-harmonic approximation, where we expect our phonon line widths to always be 0. That obviously fails, but more broadly, a quasi-harmonic approximation would expect that the effects of temperature and pressure would be additive. So put another way, the impact of pressure should not depend on temperature or vice versa. And this assumption fails insofar as we can see differences between the peaks of different colors. In particular, what we see here is that phonon line widths seem to be net decreasing with increasing pressure in gallium nitride. One way to explain this net decrease in broadening with pressure in gallium nitride comes from looking at a rescaled version of the phonon densities of states. So here we have, as usual, Wurtzite data up top, zinc blende on the bottom. This is all at 0 Kelvin on this slide. So 0 GPa doses here are plotted in black, and then I've got 30 GPa doses in pink, but these are rescaled to have the same mean energy as those at 0 GPa. And the reason they've been rescaled is to make it a little bit easier to see how peaks are shifting around. So as we've seen previously, low energy modes are shifting lower and high energy modes are shifting higher. Additionally, the band gap increases with pressure. So this is all important because it's just why phonons may not be dampening as quickly at elevated pressures. In order for phonons to dampen or to decay, they need to be able to reach the lower energy modes into which they decay. So if the band gap were sufficiently large, for example, if the lowest energy mode in the top part of the spectrum were more than twice as energetic as the highest energy mode in the lower end of the spectrum, it would be impossible for a phonon to decay into 2 lower energy phonon modes. So here the band gap is not sufficiently large to prevent 3 phonon interactions like that, but the band gap is still getting larger. So with the top and the bottom modes shifting away from one another, it's likely that there are fewer decay channels available. Now with access to fewer decay channels, the phonons would likely persist for longer. This is some similar data for gallium arsenide, but depicted differently. Here, everything is shown at 1200 Kelvin, And here I have 0 GPa data plotted in purple and 10 GPa data plotted in gray. So all dispersion relations here are plotted with line widths equal to the imaginary part of the phonon self-energy. So though there are some places where increasing pressure causes the phonon line widths to decrease, we see that pressure increases the broadening most of the time. This means that by shifting the frequencies of phonon branches, pressure is increasing the availability of phonon decay channels. To illustrate what that might look like, I provide a few examples of decay channels changing at different pressures, both at 1200 Kelvin again here. So on this slide, what I'm showing, we have source phonon modes for which we're considering the decay channels are plotted with stars. And then each plot, I've identified 2 points in the Brion zone along a given phonon branch as a source mode. So in each case, we see a source mode in gray immediately above its corresponding source mode in purple at a lower pressure. So then I have arrows connecting each source mode to pairs of destination modes into which that source mode could decay while conserving both energy and momentum. So each destination mode is plotted as a dot. So if an arrow points to a thick line, that's really a set of dots denoting that the elements of a set of phonon modes along a phonon branch could add to the elements of a partner set of phonon modes elsewhere. So these plots are showing that as pressure changes, the destination modes into which a source mode can decay often change. And in contrast, some of them happen to stay mostly the same with pressure, such as the decay channel between gamma and L, if we look at zinc blende gallium arsenide on the bottom. So in this final slide on phonon line widths, we see a summary of how phonon broadening changes as a function of temperature and pressure in gallium arsenide and gallium nitride. So here temperature is plotted on the horizontal axis. And then on the vertical axis, I've plotted the pressure impact on broadening, which I'm quantifying by taking the ratio of the amount of broadening or the sum of all the line widths across high symmetry directions at the designated elevated temperature and at 0 GPa. So a ratio of 1 indicated that there was no net impact of pressure on the line widths, and then values greater than 1 indicate that the line widths increased with pressure, and values less than 1 indicate that the line widths decreased with pressure. So the 2 lines toward the bottom of the plot are for gallium nitride, and those lines have values less than 1. So that indicates that the phonon broadening in the impact of explicit anharmonicity decreases with pressure. Now the 2 lines shown in the top of the plot are for gallium arsenide, and they always have values greater than 1. And that indicates that phonon broadening in the impact of explicitly anharmonic effects increases with pressure. So furthermore, we can see that in gallium arsenide, the degree to which pressure impacts anharmonicity decreases with increasing temperature. Okay, so takeaways from this section are that in gallium nitride, pressure decreases the phonon line widths, meaning the harmonicity of the materials goes up, whereas in gallium arsenide, pressure is increasing phonon line widths, so it's creating more phonon decay channels. So the summary of everything we've covered so far includes, and we saw that the Born stability criteria predicted the pressure, that pressure would drive instability via the same failure mechanisms for corresponding structures in gallium nitride and gallium arsenide. However, the predictions of the Born stability criteria were invalidated by the early onset of phonon instabilities in a shorter wavelength transverse acoustic mode that was found in both wurtzite and zinc blende gallium arsenide. Furthermore, temperature partially stabilized these pressure-induced phonon instabilities. Now, the softening of transverse acoustic modes with pressure increased elastic anisotropy in all 4 of the materials that I looked at here. Gallium nitride became increasingly harmonic with increasing pressure, as indicated by certain coupled pressure temperature effects on the phonon line widths. And then finally, gallium arsenide became increasingly anharmonic with increasing pressure, as indicated again by coupled pressure temperature effects, both on the phonon line widths and the phonon frequency shifts. So as for a summary of summaries, we saw a few cases of material models, namely the quasi-harmonic approximation and the Born stability criteria, failing to account for material behavior. So, in order to understand and predict the properties of materials, we need to apply approximations judiciously. And that's everything. My acknowledgement slide includes CDAC and the DOE who funded me, and then Lawrence Livermore National Lab, where I spent the second half of my PhD, and a few instrumental people in my research, including Eric Drager at Lawrence Livermore National Lab, Ola Hellman and Nina Shalemba, and then of course my advisor, Brent Foltz. So that is everything.
Well, thank you very much, Jane, for some really stimulating work, and then also the very helpful tutorial at the beginning. It was very nice.
Thought it was helpful.
It was very much. Okay, well, we certainly have time for questions. Are there any questions for Jane? I have one to start out with, Jane, and that is, so if you can think about doing experiments to access the same type of properties, information on the same type of properties. I mean, I know those experiments are really difficult. What is it about your computational methods that that allow additional information compared to what you might get from experiment? I guess what I really want to ask is, what information does your computational work access that might not be so easy to get in experiment, or might not be accessible from experiment just because of the nature of the experiments?
Mm-hmm. Well, yeah, the first, I guess, class of things are the types of conditions that you can reach in simulations. Pressure alone, for example, is, as far as things go experimentally, I suppose relatively easy, but still, quite challenging when you think about like the diamond anvil cell experiments and that sort of thing. But it's tractable, if difficult. But adding heightened temperature to a diamond anvil cell comes with a lot of significant challenges. If you start, heating diamonds, they start to degrade pretty quickly. So that's, I guess, a limitation right there that makes coupling temperature and pressure pretty difficult. Yeah, and then beyond that, I was looking at, I guess, in this work, I was really looking at, elastic and phonon stability, distinct from, thermodynamic stability. So, looking at the Wurtzite and the zinc blende phases, only one of those in each material is like the equilibrium phase for any given set of conditions, and being able to compare how those two phases sort of evolve or would evolve theoretically, can give you some intuition about, I mean, it's valuable because it can give you some intuition about how materials generally might behave. But looking at those particular materials under certain sets of conditions wouldn't be possible if the structure being considered is not the thermodynamically stable one.
Right.
May I ask you a question?
Oh, yes, go ahead.
What is the equation you found self-energy from?
Oh, I would have to look that up. That is from, so in, TDEP and its documentation outlines how it calculates the self energy. It uses the third order force constants.
You don't have any type of green functions or Dyson equation?
Let me see. I'm gonna flip through. I had extra slides. I want to see if I included any of that.
I would guess that line width should be related with the real part of self-energy. Is that right?
Yeah, let me see. Is this? Wait, how do I go back to sharing? I'm looking for the share button. Share. And then. So this is what I have. Honestly, it's been quite a while since I've looked at this, so I wouldn't be able to talk through this right now, but these were the equations that were used in TDEP. So we've got the imaginary part of the self-energy in the middle, and that's a function of these third order force constants, phi with the sub s, s prime, s double prime. And then, yeah, where the total self-energy is a function of, or a summation of the real and the imaginary parts. But, and then the bottom, the equation at the bottom shows effectively how the third order force constants are calculated.
Okay, thank you.
Yeah.
You mentioned this a little bit towards the end of the talk, Jane, but so the significance of the band gap in the phonon density of states is there, you mentioned the availability of, for example, phonon decay channels. Is there more to the phonon density of states band gap than that? It was the physical significance of it.
Sorry, is there more to it than
Just the separation of the sort of the high frequency modes and the low frequency modes, and the availability of a decay channel. For example, you mentioned that if you have a large band gap, then those decay modes are not as available, right?
Mm-hmm.
Okay, so what I'm asking is there sort of a more to the significance of the band gap in the phonon density of states than that?
Oh, I see. Well, I guess there's also that it's only as you go up in temperature, you progressively populate more more states in the first place. And you know, the larger the band gap and the higher energy the optical modes, the less likely they are to be populated at lower temperatures.
Right, sure.
So yeah, so there's that as well. But I guess that's the only other thing to immediately come to mind.
Okay, yeah, that's something that I wondered about, because, for example, for the electronic density of states, there's kind of a straightforward physical interpretation for that. But yeah, so that's very helpful. Thank you.
Yeah, thanks.
I have a question and a comment. Can I ask?
Mm-hmm.
Sure, go ahead, Mukhtar.
Yeah, this is Mukhtar Rafat from UIC. Question is, so it's the gallium nitride and gallium arsenic that also has important materials. So there are many measurements, I believe. So even elastic constants measurements. The pressure may not be as high as what you calculate. So is it possible to compare with those experimental results? Or do you know any experimental result with gallium nitride? Or I put differently.
So I didn't do any experimental work on any of the materials that I showed here.
Yeah, I know you don't do experiment, but for validate your calculation, end of the day, you still have to compare with experimental result. I mean, just a number. For example, C11, C12. You could compare what you calculated with the experiment numbers. I think there are lots of papers.
Mm-hmm. Yeah, at least for limited, normally around room temperature, or sometimes reduced temperature. There was experimental data for that. And I unfortunately don't have a plot right now doing that comparison, but I did look at those while I was doing the work to make sure things were reasonable and lined up. Yeah.
Yeah, I would think if you make some comparisons, that would be really interesting to see how calculation reflect the number can be compared to the experiment. So I have a comment. So this is a really nice plot for the elastic constant. So C11, C12. So normally, if you plot C11 minus C12 versus with pressure, that would really reflect how the shear mode softened. You independently plot the C11 and C12 for gallium nitride. You saw a spike, right? In your C11 versus pressure in your plot. Can you show your plot?
Yeah. Let's see.
You saw some spike, right?
Are you thinking of the CIG alone or when I
Yeah,
get
yeah,
to,
CIG alone.
okay.
You saw the spike. So can you show spike as well?
Sorry, can I show what?
Spike and the deep.
Oh, yes.
Yeah,
There we
so if you plot C11 minus C12, that would really show how that behaves.
Oh,
Normally in experiments, that's what you observe. If someone did experiment.
mhm.
Because in experiment, it's very hard to independently measure C12. You normally measure C11 minus C12.
I
That
see.
will show you. One more comment, maybe. So you saw some zone boundary instability in your Phonon dispersion curve, not in the gamma point, rather in the M point and K point, right?
Mm-hmm.
So that reflect if the higher pressure phase may be indicating maybe unit cell is changing. If that really happens. It's not low pressure or low temperature units, rather as maybe cell doubling or tripling or something. That would be really interesting to experimentally can be seen.
Mm-hmm.
But I thought it may be too difficult to measure. I don't know.
Yeah, I'm not sure how easily that would be to measure either.
But anyways, very nice talk. Thank you very much.
Thank you. Thanks for coming.
Okay, do we have any further questions for Jane? All right, well, if not, please everyone join me in thanking Jane Herriman for her time today and for her very helpful tutorial and to spend some time talking with us about her very elegant work. Thank you very much, Jane.
Thank you, Steve.
All right.
All right. Bye then.
All right, we'll see you next time.
See you.
All right, take care, Jane.